The following is the proof of the cosine rule, and this the cosine rule applies to triangles where there's two known sides and an included angle. Okay, so I'm going to try and get through this as quickly as I can, but I don't want to skip any detail at the same time. And it's really good to know. I think it's good to know this. For me, good mathematics is not just knowing the formulas, obviously, but where do the formulas come from? And it's nice to know the origin of these. So let's start off with a random triangle. Could be a scalene triangle of sorts, and there's no 90-degree angles, so you can't assume that. Let's label the triangle first. So let's call that vertex A, vertex B, vertex C. Not that it really matters where the B and the C go, it's the A that's important. Let's call that little a there, so set that side. Remember, the side angle pairs need to be named appropriately. That's B and that's little c. And what I'm going to do is I'm just going to draw the height, okay, of this side there. And I'm going to call this side here, I'm just going to name this vertex D. Okay, I might just take that off there for a moment. Let's call that D. I'm going to call this this length C. Sorry, just got to change this diagram ever so slightly. Let's call this side X. So AD is side X, and then DB is C minus X. Okay. So what we've done is we've set up the diagram in order to be able to then come up with the proof of this cosine rule. Basically, the idea is that if you look at the cosine rule does not contain a h, nor does it contain x. So whatever we do, and it's somewhat like the sine rule proof, you need to eliminate the h and the x somehow. Somehow come up with maybe a couple of equations, simultaneously solve them, and eliminate the h and the x, and then hopefully we'll then have a formula that relates, the a squared, b squared, c squared, the 2bc cos a somehow. So let's start off then, and we know, for example, that cos of a is x on b. So I might just write down a few things here. So cos of a is equal to x over b. Okay, so that's adjacent over hypotenuse, and b could be made the subject of the formula. Okay, so b is equal to, we'll make x the subject of the formula. X is equal to b cos a. Right, let's call that equation number 1. So now we've got a way of eliminating the x. All right, let's have a look now at, so that was the triangle ACD. Let's have a look at triangle BCD now. So that is a right angle here, of course, because that is the perpendicular height of this triangle. Let's see if we can come up now with some form of an equation that involves the h somehow, and see what we can come up with there. Now, we also know that by Pythagoras Theorem, obviously c minus x all squared, I might put that in brackets there, c minus x all squared plus h squared is equal to a squared. Okay, so we could make h the subject of the formula there. We could eliminate the x via we can eliminate the x via equation number 1 here, and then hopefully we can then come up with something that can eliminate the h. So let's do that. So by Pythagoras Theorem, we've got c minus x all squared plus h squared is equal to a squared. Okay, if we make h squared the subject of the formula, so we got h squared is equal to a squared minus c minus x all squared. Let's call that equation number 2. Okay, so you can see that x is going to be eliminated by equation number 1. So this b cos a is going to be substituted in for x. Okay, now let's have a look at back to this triangle here. We have h also can be expressed in terms of b and x by Pythagoras Theorem too. So h h squared is equal to b squared minus x squared. And let's call that equation number 3. So equation number 2 comes from triangle CDB. Equation number 3 comes from triangle ADC. These both use Pythagoras Theorem. And it's really no surprise that the cosine rule looks a bit like Pythagoras Theorem because it's based on it, actually. So why don't we equate the equations 2 and 3 together? Okay, so equating equations 2 and 3 via h squared. Okay, so if h squared is equal, so left hand side is equal to right hand side, the same left hand side is equal to a different right hand side, well, the two right hand sides must be equivalent to each other. Okay, so a squared minus c minus x all squared is equal to b squared minus x squared. Okay, let's expand that. Eventually we'll have an x showing up. We'll substitute the x for b cos a, and hopefully then we'll come up with the formula that we're intending to prove. Okay, so a squared minus, so let's expand the c minus x all squared. So that's c squared minus 2cx plus x squared, okay, is equal to b squared minus x squared. Let's expand the bracket again and factor in this this negative sign. Okay, so a squared minus c squared plus 2cx minus x squared is equal to b squared minus x squared. Now you can see that we can straight away eliminate the x squareds from both sides. Okay, and while we're at it, why don't we move the negative c squared and the positive 2cx over to the right hand side. So we have a squared is equal to b squared plus c squared minus 2cx. But what do we know about x? So let's call this equation number 4. What do we know about the x? The x comes from here. Okay, so this equation is going to be substituted, as in the right hand side of equation 1 is going to be substituted in there for x. Okay, so a squared, okay, is equal to b squared plus c squared minus 2c times, okay, b cos a, and you can see that basically is the cosine rule. Okay, so if we swap the b and the c around, since it's all multiplication, I could, if I wanted to, just write it this way, and we have our cosine rule. A squared equals b squared plus c squared minus 2bc cos a.